In our last video, I asked you why the chicken crossed the basketball court, and it was because the referee was calling foul. In this video, why did the tortoise cross the road? Well, he wanted to get to the Shell station on the other side. This is another easy section that we're doing today. This is section 10.9, where we're dividing radicals. And you have already done all of the basic foundation work for this when you learned to rationalize a denominator, which is where you learn that if you had a radical symbol in the denominator, that you had to do something called rationalize it, which meant you had to eliminate that radical sign in the denominator. In this particular case here, if we multiply by the square root of 7 divided by the square root of 7, what we're looking for is so that if we have a square root in the denominator, our radicand here, which will be 49, becomes a perfect square. So the square root of 49 is 7. You have 2 times the square root of 7 divided by square root of 49, which is 7. 2 times the square root of 7 divided by 7. And from our multiplicative property of identity, where it tells us that anything that we multiply by 1 might change its appearance, but it doesn't change its value. And any number divided by itself is also equal to 1. So even though we're changing significantly the appearance of this expression, we're not changing its value, because all we're doing is multiplying that expression by value, square root of 7 divided by the square root of 7, which is equal to 1. What we're looking for in the denominator when we multiply by a radical is we're looking for perfect squares. In this case, if this had been the cube root of 7, we'd want to multiply by something here that would give us a perfect cube in the denominator. Let me just go ahead and show you that one right now briefly. If we had 2 divided by the cube root of 7, you remember that when you are looking for a cube root, you're looking for a factor that is used 3 times. So we need to have 3 factors of 7 underneath this radical sign. And how many factors of 7 do we have underneath the radical sign now? Well, we have 1 factor. So how many more factors do we need? That's right. You need 2 more factors of 7 underneath the radical sign. What root are we taking? We're taking our cube root. So we are going to multiply 2 divided by the cube root of 7 by the cube root of 7 squared times the cube root of 7 squared. Gives us 2 times the cube root of 7 squared divided by the cube root of 7 cubed. Okay? Cube root of 7 cubed is 7. So our solution to this problem, which I'm going to write up here, 2 times the cube root of 49 divided by 7. This might seem like I really pulled a strange one out of thin air. This is very representative of what you're doing when you're rationalizing a denominator. You can't simplify that 49. Don't think, oh, well, that's supposed to be a 7. What is, if you have a square root. But what you have here is the cube root. So what happens if instead of simply having a single radical in the denominator, you have a binomial in the denominator? For example, we have, this is number 1, 4 divided by the square root of 2 minus 1. We can't just multiply this by the square root of 2 divided by the square root of 2. because, let me show you what would happen. Square root of 2 times square root of 2 minus 1. Square root of 2 times the square root of 2 is the square root of 4, which is 2. But now we have the square root of 2 minus 1 times a negative 1. So we still have our radical in the denominator. Doesn't help us at all. But using that really cool special product, the difference of two squares, where if you have two factors, two binomial factors, that the only difference between them is the sign. When those multiply together, you have a squared minus b squared. So we want to multiply this by the square root of 2 plus 1, because this will give us the difference of two squares, which will eliminate the radical symbol. If we're going to be able to legitimately do this, the only way that we can multiply is by having the same expression in the numerator as we do in the denominator. What this expression is called here, this is the square root of 2 plus 1, this is called the conjugate. You have to know this vocabulary, conjugate. And this says that the conjugate of a radical expression is the radical expression with the opposite sign between the terms. If you had square root of 2 plus 1, its conjugate would be the square root of 2 minus 1. When you have the square root of 2 minus 1, the conjugate is the square root of 2 plus 1. In other words, it's the missing factor that will give you the difference of two squares. So this works out really nicely. Multiply the numerators together. Whoops. Multiply the denominators together. Because you have the difference of two squares, it's the first term squared minus the second term squared. 4 times the square root of 2 plus 1 divided by 2 minus 1. That shows up a lot. 2 minus 1 is 1. Our solution is 4 times the square root of 2 plus 1. Now, what's wrong with this? 4 times quantity of square root of 2 plus 1. What's wrong with this? Well, that's right. I still need to distribute the 4. 4 times the square root of 2 plus 4 times 1 is 4. That's all there is to multiplying these. It's really cool to use the conjugate of a radical binomial because it eliminates your radical signs in the denominator. So let's go ahead and do another example that they have right here in the book. And remember that we did several examples in class that were actually from your homework problems, so you really should be very well prepared for this lesson. So look at example number 2. I'm going to pick it up and make sure that I get it right. 3 times the square root of 2 plus 4 divided by square root of 5 plus the square root of 3. Let's see. 3 times the square root of 2 plus 4, square root of 5 plus the square root of 3. What's the conjugate going to be here? Since we have more than one term in the bottom, we're going to have to multiply the conjugate. The conjugate is this radical expression itself with the sign changed. Square root of 5 minus the square root of 3 divided by square root of 5 minus the square root of 3. You now have in the denominator the difference of 2 squared. Square root of 5 squared minus the square root of 3 squared is 5 minus 3. In the numerator, we're going to have, 5 minus 3. In the numerator, we're going to have to FOIL. We have 3 times the square root of 2 times the square root of 5, which is 3 times the square root of 10. The outside terms, 3 times times the square root of 2 times the minus square root of 3. So we're going to say plus 3 times the square root of 2. And I'm going to go ahead and write out what we're doing. 3 times the square root of 2 times a negative square root of 3. Our inside term, plus 4 times the square root of 5 plus 4 times minus square root of 3. Okay? Having a little bit of a hard time looking at my board. There's a glare on my board that you guys aren't being able to see. So what we have is 3 times the square root of 10. What are we going to multiply here? Well, we have the square root of 2 times square root of 3 becomes square root of 6, a negative and a 3. So we have minus 3 times the square root of 6 plus 4 times the square root of 5 minus 4 times the square root of 3. All of this is over 2. Now, what in the world do we do next? There surely in this mess is something that we can simplify. 3 times square root of 10. No perfect squares in there because this factors into 2 times 5. 6, no perfect squares. 5 is prime. 3 is prime. There's no common factor of 2 up here. Believe it or not, make sure I got everything correct. This is the simplified form, or the proper form, whatever you want to call it, of this expression. We started off with 3 times the square root of 2 plus 4 divided by the square root of 5 plus the square root of 3. Does this look a lot messier to you? To me, it looks a lot messier. But our rule tells us that we're not allowed to have a radical sign in the denominator, and we don't. So that's the solution to example number 2 from page 432. Let's go ahead and look at example number 3. I really think this is pretty redundant. It's just illustrating the same thing. But I think part of what they're doing here is just getting you accustomed to manipulating radicals, manipulating expressions. Example number 3 says the square root of m minus the square root of n. I don't like m's and n's because it's hard to distinguish between them. My m's tend to have 3 humps. Divided by the square root of m plus the square root of n. Okay, now the first thing you need to do is realize, oops, can't do this because I have radical signs in the denominator, which means that I'm going to need to simplify those. And then the next thing one of you might see is, we've got square root of n plus n, square root of m minus the square root of n. These two factors are the difference of 2 squares. That is correct. If these two were factors, it would be the difference of 2 squares, but they're not. We've got a division symbol here. We want to have our factors in the denominator. So we need to multiply by the conjugate of the square root of m plus n. The conjugate is the same expression, different sign. So we're going to multiply by the square root of m minus the square root of n divided by the square root of m minus the square root of n. And the reason that we do that is because we have to multiply by the conjugate. It has nothing to do with the fact of that we have square root of m minus n in the numerator. Had that extra extended line there. It was confusing. That's not a negative. It's not this expression minus this. Remember that we have to multiply by the conjugate. So we have square root of m times the square root of n squared. Since that factor is being used twice, you can go ahead and use FOIL and multiply it out, or you can remember that that's a perfect square trinomial. So your numerator is the first term squared minus 2 times the product of the first and last terms. We have a minus sign here, which is where we got this minus sign, plus the square of the last term, plus square root of n squared, divided by, we have square root of n plus n times the square root of m minus the square root of n. So you have the difference of two squares. So you have the first term squared minus the second term squared. First term squared minus the second term squared. Make sure that you get your radical symbols. There's a big difference between the square root of m squared and m squared itself. Okay, now what you have, the square root of m squared, radical here, the root is squared. The solution to that is simply m minus 2 times the square root of mn minus 2 times the square root of, we use our product rule here for radicals, m times n plus the square root of n squared is n. Square root of m squared is m. Square root of n squared is n. Now, the book says our solution is m minus 2 times the square root of mn plus n. In the denominator we have m minus n. Now something some of you might think is, oh, we can cancel common factors, so I can cancel the m's and I can cancel the n's. Well, you can't. It is true that you can cancel common factors. This is okay. You cannot cancel, however, when you have terms. This one right here says no way. What we have here is we have 3 terms in the numerator. We have 2 terms in the denominator. You can't cancel the m's or the n's because they're not common factors, they're terms. So that's really all that you need to be looking for with section 10.9.